Hello. So as you can see, it's raining outside. It's also very late at night, because this is the only time when I could see it raining. Now, I have a container here, which I've measured the area. I'll go through a calculation of that afterwards. So I'm gonna put this out in the rain for 10 minutes, and afterwards I'll come back and we'll see how much rain is inside. Now, you probably don't want to see it raining for 10 minutes, so I'm gonna put it down here, and we'll come back in 10 minutes. Hello. Last time we said that we would leave the water outside for around 10 minutes. Unfortunately, I came back after 10 minutes, and I realized that that greatly overestimated the rate at which the water was falling and how fast it would accumulate in the container. So this is actually left out overnight, around 5.5 hours. I was able to get a fair amount of water, not a lot, but you can see it if I slosh it around a little. Now, the cross-section area of the container is 15 centimeters by 15 centimeters. We need this so that we can multiply it by the height of the water in the container and find out the volume of the water in the container. Unfortunately, there will be a small error associated with this because, as you can see, the container has a rounded bottom, so the actual volume is going to be a little less than that. Regardless, this is all like a fairly rough calculation. I don't think it makes too big of a difference. Now, if you can see at the side, it's a little difficult to tell because the ruler doesn't exactly match up on the camera, but it's around 2 centimeters of height, 1.8 centimeters of height of the container, of the water in the container rather. So now, I'm just gonna go through a little bit of a calculation to find out how much energy is in the water. Hi, so the main energy that's released in the rain is Q equals ml. Now the reason that this is the main equation is because this is the amount of energy that's released when a gas condenses. In the sky, the rain is in water vapor. When in that area it reaches its maximum 100% relative humidity, it will gather into a cloud. And then, upon some further stimuli, it will condense into a liquid, first at 100 degrees Celsius, and then it'll cool down, and that'll release more energy. So the total energy is actually this plus the energy released as it cools down, but we can use a combined value for both the vaporization, the condensation, and the cooling down. We're going to use L equals 2600 kilojoules per kilogram. Now, we only know the volume of water in the container. We need to also find the density so that we need to know the density so that we can determine the mass. So the density, everyone knows, is 1,000 kilograms per meter cubed for water. Now, we can express this as terms of Q equals rho VL, and Q equals 1,000 kilograms per meter cubed times 0.15 meters times 0.15 meters, that's our cross-section area, times 0.018 meters, that's our height, times 2600 kilojoules per kilogram. Now this will get us around 1.053 kilojoules. Now you're going to say that's not a lot, and it's not, but it was also not raining for very long, not raining very hard. It was only a very small area. If you took a thunderstorm for its entire duration and took it over the entire area over which it was raining, and you gathered up all that water, the energy you would find that was released as it rained could be on the same order of magnitude as an atom bomb. Thank you.